Lesson 4 of Chapter 10 is on mathematical induction. This is a method of proving something to be true. Before I get into that, I was reminded of a joke that I heard. What do you get if you cross a mathematician and a clock? You get arithmetics. They just keep getting better, don't they? Alright, so principle of math induction has a three-step process. It starts off with step number 1, showing that something works for the first case. We call this the base or the anchor step. Then step number 2 is assume that it works for any particular case. This is your inductive hypothesis. And then step 3 would be to show that it works for the next case, which is your inductive step. It's kind of like this. To understand why the principle of mathematical induction works, imagine a ladder with an infinite number of rungs. If you can get on the ladder, which would be your anchor step, and then move from one rung to the next, if you're physically able to do that, which would be your inductive hypothesis, then you can climb the whole ladder. Similarly, imagine an unending line of dominoes, like you can see on the right, arranged that if any of the nth domino falls, the nth plus 1 domino will also fall. And so by pushing over the first domino, you start a chain reaction that knocks down the entire line. So here's the kind of problems we're going to be doing. That's a three-step process. And so you can see that we've got an infinite arithmetic series, 3 plus 7 plus 11. You can see the pattern as it goes up by 4. This would represent the nth term. This represents the sum of the first n terms. And so the first step, step A, is to show true for n equals 1. This is our anchor step. So if we put 1 in for n, we get 4 times 1 minus 1 equals 2 times 1 squared plus 1. Well, the left-hand side gives us 4 minus 1, which is 3. The right-hand side gives us 2 plus 1, which is also 3. So the first step is fairly simple, putting 1 in for n. Now, step B, the second step, is we have to make an assumption. We're going to assume that if we take 3 plus 7 plus 11 and keep adding terms until we get to the nth term, which we can see is 4n minus 1, that it does in fact add to give us 2n squared plus n. We're going to make that assumption. And then our third step, step C, is to prove that if we add the first n terms and then add the next term, we're going to get a new summation. So if this is the nth term, the next term after that would be 4 times n plus 1 minus 1. And our new summation would be 2 times n plus 1 squared plus n plus 1. So now, since we had made the assumption that these first n terms adds up to give us 2n squared plus n, that's from step B, plus this next term, I'm going to distribute to get 4n plus 4 minus 1. That should combine to give us, let's see here, if I distribute, I get n squared plus 2n plus 1. And so now combining like terms, looks like we get 2n squared plus 5n plus 3 on the left, and on the right, combine like terms, we get 2n squared. 4n plus 1 gives us 5n, and then 2 plus 1 gives us 3. Since the left side equals the right side, we have proven this by math induction. Next example, same kind of problem. So, step A is to show true for n equals 1. So we can do this by putting 1 in for n. So 3 times 1 minus 2 should equal 1 times 3 times 1 minus 1. Well, the left-hand side gives us 3 minus 2, which is 1. The right-hand side gives us 3 minus 1, which is 2, over 2, which is also equal to 1. Step B, we make an assumption. We're going to assume that if we add up the first n terms, and the nth term here appears to be 3n minus 2, that it does in fact add together to give us n times 3n minus 1. And then we're going to try and prove that if we add the first n terms, and then add the next term, that it gives us a new sum. So, if this is the nth term, the next term after that would be 3 times n plus 1 minus 2. And our new sum formula would be n plus 1 times 3 times n plus 1 minus 1, all divided by 2. And so now we made an assumption that these first n terms adds together to give us n times 3n minus 1 divided by 2. We add this next term, which if I distribute gives us 3n plus 3 minus 2. That should combine to give us, let's see here, that's going to give us 3n plus 3 minus 1, which is 3n plus 2, all divided by 2. Simplifying now, if I multiply everything by 2, I'm going to get rid of my fraction, so I'm going to do that now. I'm also going to distribute, so that gives us 3n squared minus n plus this next set of parentheses simplifies into 3n plus 1 multiplied by 2 gives us 6n plus 2. And then foiling the numerator there gives us 3n squared plus 2n plus 3n plus 2. We multiplied everything by 2, so we got rid of that fraction. And now combining like terms, we got 3n squared plus 5n plus 2 on the left, and on the right, 3n squared plus 5n plus 2. This proves that this is always true. Let's go to this one. This is a geometric. You can see here that the pattern is we're multiplying by 2. So we have the first step, show true for n equals 1. If we put 1 in for n, we'll get 2 raised to the 1 minus 1, and that should equal 2 raised to the first minus 1. Well, the left-hand side gives us 2 to the 0, which is 1. The right-hand side gives us 2 minus 1, which is 1. Now we make an assumption. We assume that if we add up the first n terms, and the nth term is 2 to the n minus 1, that it does in fact add together to give us 2 to the n minus 1. Then we're going to try to prove that if we add the first n terms, and then add the next term, we should get a new summation. So, if this is the nth term, the next term after that would be 2 to the n. And our new summation would be 2 to the n plus 1 minus 1. Since we made the assumption that these first n terms adds together to give you 2 to the n minus 1, then we add this next term, 2 to the n, it should give us 2 to the n plus 1 minus 1. Well, right here, this term and this term are like terms. So we can combine those terms since they're like terms, and we get 2 times 2 to the n. Still got the minus 1. And then there's an exponent of a 1 on this 2, and so now, since we have two terms with the same base being multiplied, we can add those exponents, so we get 2 to the n plus 1 minus 1 equals 2 to the n plus 1 minus 1, and both sides equal each other, thus this is always true. Alright, last example is, you can see here the pattern is not arithmetic, it's not geometric. We're going to try to use math induction to prove that this is always true. So we start off with step A, trying to show that it's true for n equals 1. And if we do that, we put 1 in for n. So we get 2 times 1 minus 1, all raised to the second power, should equal 1 times 2 times 1 minus 1 times 2 times 1 plus 1, all divided by 3. And so it looks like the left-hand side gives us 2 minus 1, which is 1 squared, or 1, should equal, we get 1 times 1 times 3, all divided by 3. Our second step is to make an assumption. We're going to assume that if we add 1 plus 9 plus 25 till you get to the nth term, which is 2n minus 1 quantity squared, that this would in fact add together to give us n times 2n minus 1 times 2n plus 1, all divided by 3. So now we're going to try to make a proof statement. And our proof statement is going to say that if we add the first n terms, then add the next term, that it is in fact going to give us a new summation. Well, let's see here. If this is the nth term, the next term after that would look like this. 2 times n plus 1 minus 1 quantity squared. And my new summation would be n plus 1 times 2 times n plus 1 minus 1 to, I got to simplify because I'm running out of room here. So 2n plus 2 plus 1 gives us 2n plus 3, all divided by 3. We assume that these first n terms multiplies to give us n, 2n minus 1, 2n plus 1, all divided by 3. Then we add this next term. Let's simplify that. So that gives us 2n plus 2 minus 1, or 2n plus 1 quantity squared. And if I simplify this, we got n plus 1, 2n plus 1, 2n plus 3, all divided by 3. I'm going to try to show the left side equals the right side with the amount of space I have here is going to be challenging, but let's see if we can do it. We're going to have to multiply everything by 3, and I'm going to have to FOIL out the numerator of this first fraction. So we're going to get 2n squared minus n multiplied by 2n plus 1. Multiplying everything by 3, so that 3 in the bottom is gone. We'll have 3 times, if I FOIL that, I'll get 4n squared plus 4n plus 1. And multiplying by 3 over here is going to eliminate that fraction, and if I FOIL the first two, we get 2n squared plus n plus 2n is 3n plus 1. Still got the 2n plus 3. And now, FOILing this gives us 4n to the third. We would have 2n squared minus 2n squared would cancel. And then we'd have negative n. And then, if we distribute, we'd have a 12n squared. 12n plus 3, and this should equal, foiling